Let's start on lecture 26. We talked about unconditional jumps, like go to and bra W. We also talked about call and go to instructions for subroutines, call or call W, and return LW, return from interrupt. And then we spent a fair amount of time on conditional branch instructions. Conditional execution in PIC is essentially skip the next instruction if condition is true. It takes two general forms. It can test bit and skip if the bit is cleared or set. You can also do increment and decrement a register and skip the next instruction if the result is 0. So we have these four instructions. First two doing the bit test, BTFSC and BTFSS. So that is to skip if it's clear and skip it if it's set. They take two operands. First is the register F, and then comma B. B is a value from 0 to 7 to indicate which bit in that register we want to do the test. The next two instructions, decrement FSZ, is to decrement a register F, putting the result in F or W, and it will skip the next instruction if the result is 0. On the opposite, you can do increment INC FSZ, which will increment register F, put the result into F or working register. Again, it will skip the next instruction if the result is 0. There are some other instructions we might use in our actual design. For example, clear watchdog timer. Watchdog is a hardware mechanism to restart the microcontroller if something went wrong. Sleep will make the microcontroller go into standby mode to reduce power consumption. Reset is to perform a software reset so that the microcontroller can start from the beginning. Also, tree F is to copy the working register to try register. It's getting obsolete and it's not across all the PIC microcontrollers, so when you use it, be cautious. Also, option or NOP instructions for basically consume clock cycles without affecting the operation. Now, we would like to talk about differences between PIC microcontroller assembly language and the x86 Intel's assembly language. There's one major difference. In a PIC microcontroller, we cannot do simple data transfer or operation on two registers. Here, by registers, we mean two registers other than the working register. For these operations involving two registers, it has to involve the working register W. And we have some examples here. In these examples, we first have the x86 assembly language instruction, then we see how we're going to implement the same function using PIC assembly language. First example, move AL, BL. This is to copy the value from BL to AL. And let's assume that we declared AL and BL as registers in PIC. And so if we want to do the data copy from register BL to AL, we actually have to use two instructions. First is to move F, BL, W. Move F is to copy the value from a register to either the register itself or the working register. Because of this W, this indicator tells the microcontroller that the value of BL is going to be copied into the working register. And the next instruction is to copy the value from the working register to another register, and in our case, this is AL. So we're going to copy the value from the working register to AL. With these two steps, we can copy the value from from BL to AL. Similarly, for addition instructions, add AL, BL. This is an instruction for Intel assembly language. And to do the same thing, to do the same operation in pick, we will need to use two instructions. First is to copy the value from BL to the working register. And the second instruction, add WF, is to do the addition operation on the working register and AL, and the result is going to be put into AL because this comma F. Condition jumps. In x86, we have a single instruction to perform the condition jump. While in PIC microcontroller, the basic condition jump are combinations of bit test and skips. And the condition you are testing is in fact the opposite of jump condition, because remember we do the skip. We have two examples here. For x86, we can do JNC label. JNC is jump if not carry. So that means if we have a 0 on the carry bit, we will jump. That's not carry. If we have a 1 on the carry bit, we will not jump. So let's see, to implement the same operation, how we're going to do it in PIC. So we do bit test a register, skip if the bit is set. That's SS. We're going to test the carry bit in status register. So you see here status, comma C. We will skip the next instruction if C is set. On the other hand, if C is 0, this bit test will fail. And because that's to check whether it's set. If it is 0, that's not true. So we will not skip the next instruction. That's exactly what we want to do. We want to go to label. So this example helps you to understand what we say here. The condition you are testing is the opposite of the jump condition. And JE label is similar. JE stands for jump if it's equal, and by equal we really mean that the 0 flag is a 0. I'm sorry, 0 flag is a 1. So what we have here is we're going to test the 0 flag, and we will skip the next instruction if 0 is a 0. Well, 0 flag is a 0. I should be clear on that. And if 0 flag is a 1, this condition is not true, so we'll not skip the next instruction. So that is to go to label. To evaluate other conditions, we may want to use subtraction in place of compare. So in x86, we use CMP X, Y. In PIC, we'll use move F, Y, W, and subtract W, F, X, W. So these two instructions actually do subtraction and subtract Y from X. The possible results for unsigned, you can probably see X when x is greater than y, you see 0 flag is a 0, carry flag is a 1. If it is equal, 0 flag is a 0, carry flag is a 1. And then x less than y, and 0 flag is a 0, carry flag is a 0. For more complex conditions, and we have the conditional code here. For shift and rotate operations, we'll need to account for a bit being shifted and rotated out. In x86, basic rotation does not rotate through the carry bit, and we can either pretest or fix the value later. And for multi-bit rotation and shifting, we need to use loops, because for pick we only do 1 bit, either rotation or shift. So if you do multi-bit, you have to do a loop. Let's look at this example. Again, these examples starts with the rotation instruction in x86. Then we use pick instructions to implement the same function. First example, rotation to the right, AL, 1. This is to rotate the bits in AL register to the right for 1 bit, and this instruction will update the carry flag. Actually, will not update the carry flag. So what we do here is, first, we would like to first clear the carry flag, and then we do the rotation to the right for 1 bit. RRF is to rotate to the right for 1 bit. AL, F. AL is the variable name, F is the register. So we're going to update the value of the register. And the next instruction is, we will do a bit test and skip if the carry flag is a 0. Because this RRF is going to actually update the carry flag. So what we want to do here is, we want to keep the original value of the carry flag, because ROR does not touch the carry flag. So we'll do the test. We will skip the next instruction if C is clear. Because that's what we would like to keep. Because carry flag is supposed to be 0 for our case. And if the carry flag is a, let's see here. If the carry bit is 1 after the rotation, okay, because this RRF could change the carry flag to 1. And if that's the case, what we're going to do is, actually we're going to handle the case where carry flag is 1. So this instruction will not be skipped. So we're going to do BSF AL, 7. So we're going to set the MSB of AL to 1. In the next example, we do RCL. This is actually going to go through the carry bit. And here we do AL, 3. That is to say, we're going to rotate through the carry bit to the left for 3 bits. This is a multi-bit. So you can see this is our first example of loop structure in a pig. It's similar to what we do in x86. We will initialize the counter by loading 3 into working register W and copy the value from W to this count. Let's assume count is a register declared somewhere at the beginning. So count going to keep the number of iterations we have gone through so far. Loop RLF AL comma F. So we're going to rotate AL to the left for 1 bit. And this rotation is going through the carry flag, so we don't have to worry about the carry flag anymore because this RCL is going through the carry flag. Again, what we're doing here is we want to translate the Intel assembly language instructions into PIC instructions. At the end of the loop iteration, we do decrement. So we decrement count, and we will update that variable. So this is comma F is for. So we're going to update the variable by decrementing by 1. We will skip the next instruction if it becomes a 0. What is the next instruction? It is go back to the beginning of the loop to do the second iteration or the next iteration. So for this case, how many times this RLF will be executed? 3 times. Because first time, when we get here, AL is, well, this count is 3. So we will do the RL first time, and after that, we do decrement, count becomes 2. Go back, we do RLF second time, and we decrement count, that becomes 1. It's still not 0, so we're going to go back to the third time, RLF. And this time when we decrement, count becomes 0. So this DECFSC, the condition is true. So we're going to skip this go to instruction. So we're going to go to the next one. Here I have a few more examples of Intel 36 assembly language instructions, and I would like you to work on these examples to translate them into PIC assembly language instructions. And let's assume that these registers ALH are declared somewhere at the beginning using C blocks for the PIC. So in the instructions, you can use them directly. I'll give you 1 minute to work on these instructions. Well, the idea here is to, because for PIC, it cannot do these operations or sub on 2 registers directly. You have to use the working register to store one of the variables and perform the operation with the working register. So to translate these instructions, the first PIC instruction you want to use is to move F, one of the registers, comma W, that is to copy the value of the register into the working register. Okay, let's look at these instructions. First one, OR AL, comma BL. This is to do logic OR operations on AL and BL. As we said earlier, that in PIC, we cannot do these OR operations on 2 registers directly. We have to use the working register as a medium. So the first instruction we do is move F, BL, comma W. This is to copy the value of BL to W. Second instruction is IOR WF. IOR is the logic OR in PIC. And the operands are AL, comma, F. This is to do OR operation on two numbers. One comes from the working register, and the other one comes from AL. This comma F, this F indicates the result needs to be put into the register, and that's AL. Subtraction BL, comma, AL. So what we're going to do here is to subtract AL from BL and put the result into BL. That's what we do in Intel processors using this instruction. So first we want to get the value of AL into the working register. So we do the same as in the first case. We move F, AL, comma, W. So the value of AL goes into W. Second instruction, sub WF space BL, comma, F. This is to subtract W from BL, and we know W has the value of AL, so we're essentially doing BL subtract AL. This comma F, again, F is an indicator to say we want to have the result stored in BL. J and Z label. Jump if it's not 0. This J and Z will test the 0 flag. If the 0 flag is a 0, we will jump to that label. We'll do the bit test. We know the 0 flag in status. That's the bit we want to test. We do bit test register, skip if it's set. Remember, it's opposite to really what we want to check because we are doing skip in a PIC. So if this 0 flag is a 0, this condition checking will be, it will, if this 0 flag is a 0, this, because it's S here, that's set, so that's not true. So we'll skip a not skip. We do not several times. We will not skip the next instruction, right? If that condition is not true. We will skip if the condition is true. So that's how we get to the go to label. This JB is actually checking a combination of the 0 flag and carry flag. So it's a bit one more step compared to the previous examples. I'll skip this example. Next example is the rotation, and here we're rotating multiple bits, and we are doing the rotation not through the carry bit, so we'll have to do additional checking to make sure that it's not going to be updated. The carry flag is not going to be updated, and again, I will skip this